So here is a problem from the previous AP exam questions, and it was in 1983, B4 question. You have PV diagram that represents the states of an ideal gas during one cycle of operation of a reversible heat engine. The cycle consists of the following four processes. From A to B, it's a constant temperature and it's given 500 Kelvin. So it says isothermal. From BC, it is adiabatic. So that means no heat entered or leaves the system. From C to D, it's a constant temperature. And it's given 200 Kelvin. So temperature doesn't change, isothermal. And then again from D to A, it's adiabatic. During the process AB, the volume of the gas increases from V sub 0 to 2V sub 0, so it increases twice. And the gas absorbs 1,000 joules of heat. So this is our question, just a statement was given. Now the questions. In A, they ask, the pressure at A is P sub 0. So the pressure at A is P sub 0. You have V sub 0 and 2V sub 0. And here are your points. A, B, C, and D. So the pressure at A is P sub 0. Determine the pressure at B. So for A part, I can use PV over T is equal to PV over T, right? So I have the gas law, P1 V1 over T1 is equal to P2 V2 over T2. And in my case, it is P sub 0, V sub 0, temperature is constant, is equal to P V 2 times V sub 0. Because at A, my pressure is P sub 0, V sub 0. And at B, it's twice V sub 0. And I'm looking for the pressure at that point. So that gives me P at point B is equal to 1/2 P sub 0. So that is our A. For, let me just keep formulas in red. So that is A. For B, they ask, using the first law of thermodynamics, determine the work performed on the gas during the process AB. Because it is isothermal process, change of the temperature is equal to 0. If the temperature doesn't change, so does the internal energy of the gas does not change. So from the formula, we have the internal temperature of the gas is equal to the heat added into the system plus the work, or minus the work done on the system or by the system. So looks like it is the work is going to be equal to the heat added into the system. And let me talk to you about, let me do this way. Let me rewrite it. I have a 0 equals to heat added into the system, so that's positive because heat is given. Heat is added into the system. Heat is added into the system, so I know that number. And the work done, the volume is increasing. If the volume is increasing, then the negative work done on the gas, positive work done on the environment. So that is going to be plus the work, but then the work is equal to negative Q because the work is done negative and equals to negative 1000 joules. Because Q is added to the system is 1000, so that gives me negative 1000 joules. For C part, during the process AB, does the entropy of the gas increase, decrease, or remain unchanged? So for C, the entropy has a formula. So the change of entropy is equal to the heat change over the temperature. The heat is added into the system, so it is a positive number. And the temperature stays the same, 500. So the heat or the entropy of the system increases, and it is equal to 2 joules per Kelvin. So we can say that the entropy of the gas increases because Q is positive, it's added into the system, and the gas is also expanding, so the entropy is increasing. The entropy is increasing. For T part, they ask you calculate the heat C given off by the gas in the process of CD. Let me go back to look at CD. Do you see that CD is also isothermal and temperature is 200 Kelvin? So if the temperature doesn't change, again, there is no internal gas energy changes. So going back to D part, so Q in is equal to NR T. Let me do it this way. We have this formula. Delta U is equal to Q in plus the work or minus the work done on the gas. Because our delta U is equal to 0, since there is no change of the temperature on CD and AB, right? So it's just an isothermal process. We have that Q in isothermal process is going to be the work done by the gas, and we have to decide whether it's negative or positive depending whether there is expansion or contraction of the gas. And the work is equal to three halves N R delta T. So this would be for the hot reservoir. So that means this going from B to C. And Q cold is equal to the work, because there is no change of internal energy, is equal to 3/2 and R delta T. And this one is from C to D. And I can use this trick when I divide one side by the other side. And I get Q hot over Q cold is equal to 3/2 and R can cancel, and I have delta T BC over delta C CD. In other words, I can say Q hot over Q cold is equal to T hot over T cold. Then if I plug in my numbers, I'm gonna get T cold, Q cold is equal to Q hot, T cold divided by T hot. So this one is 1000, this one is 200, and this is 500. So Q cold is 400 joules. And I just want to mention here something. In this case, the heat is added into the system. So this is Q hot. And in this case, the heat is leaving the system. And you see this is Q cold. And I can also place a negative sign right here, because this is heat taken out of the system, not added to the system. And finally, the last part, E. So we just solved for D. Now the E part. During the full cycle A, B, C, D, E, is the total work performed by the gas by its surroundings positive, negative, or zero, and justify why. Because our, let me choose one color here. Because our area right here, or I should say this is the full cycle to go from A to B to C and back to A. It goes all the way back to A. I can say that the total internal energy of the gas over this process is going to be equal to 0, because we started with A, we ended up with A. And then again, if I use the law of thermodynamics, the internal energy of the gas is equal to heat added or taken away from the system, and plus the work done on the system. And in this case, I have 1000 joules of energy added into the system and 400 joules of energy taken away from the system. So the work done by the gas is equal to 600 joules. But the work done by the gas on the surrounding is 600 joules. If you remember this graph, you have hot and the energy is coming from here. Q hot is coming into the engine. Some of it is going to be spilled back into the cold, the reservoir. This is T cold, this is T hot, this is Q cold, and the work is going to be done on the surrounding. So this is work. So because the work is done on the surrounding is equal to 600 joules, it is positive work on the surrounding, but it is negative work for the gas. So if they ask you during this process, the total work performed on the gas by its surrounding, the way they ask, performed on the gas by its surrounding, let me do it this way so it makes sense why. Performed on the gas by its surrounding is negative. The work done, so this is the work done on the gas. So the work done on the gas is negative. The work done on the gas is negative. The work done by the gas on the surrounding is positive. So it's really important to see the way they ask you a question when they ask this type of a question.